And welcome back to examples. Let's see what we can do with these spring equations, or simple harmonic mostly. So now we have a block, 2 kilograms, attached to a spring, a horizontal spring, and it's going to go back and forth. It has an angular frequency of 3 radians per second. What's the spring constant? Well, we know that the angular frequency is just square root of k over m, where k is your spring constant and m is your mass. We know the mass. We'll solve for the spring constant and plug it in. Real quick note on units. A joule is a derived unit. It is actually a kilogram meter squared per second squared. So when we have a joule per meter, so a joule per meter squared is equal to a kilogram meter squared over second squared over meter squared. And you can see that these units right here, let's use yellow so it shows up a little better, that meter and that meter canceled, which is what happens, kilograms per second squared. Radians don't really have units. We just put it there because we like to have something put there. Example 2. Now you have a 3 kilogram block attached to a spring. 3 kilograms. All right, it has an oscillation period, so t is equal to 1.5 seconds, and it's initially displaced 7 centimeters. What's the maximum velocity and acceleration? Well, we start with the formula for position, and we want velocity. We know time, so we can get omega from our time, period. And I get omega, angular frequency, is 2 pi over 1.5 seconds, or 4/3 pi. Now we want velocity. Velocity is the derivative of position. So we're going to plug this in here. And I said I wanted the maximum velocity. Well, the maximum value that cosine can have is if that equals pi, or at, which has a value of 1. All right, so I just plugged in 1 there because that's as big as cosine can get. And I solve for my max velocity. Alternatively, you could look at this via energy, which is something we've always been doing, at least in this class. Now we know that at max kinetic energy is just when it's all kinetic energy. So your total energy for the system is all kinetic energy. In other words, nothing's stored up in the spring. Now what we do, those 1/2 will cancel, and we just set up total energy, Ka squared equals to Vmax squared. Solve for Vmax. All right, omega A, which if we look, omega A, same thing. We're good. If it got out to be something different, that'd be a reason for concern, but we're okay now. Now let's look at the acceleration. Now acceleration we define as the derivative of velocity, so we take the derivative of that formula, the one we had for velocity before. Okay, now I've got this negative sign, and again I'm looking at the maximum. Well, in order to get a maximum, I need a minus here, sorry, that minus went away. That's going to be a plus, that's going to be a plus. And what's going to happen, well, now we've got this omega squared term. So I get 0.124 pi squared. The trick is whenever you're looking for a maximum, sine and cosine are great because their values are -1 to 1. You can figure out what the max of that is reasonably easy. Now for the final example. So in this case, same thing, horizontally mounted springs. We'll get into vertical springs later. But horizontally mounted spring, the equation for the position is given below, which is this position. What's the magnitude of the acceleration of the system? At what time? So this is a little bit different. I'm looking for time. Well, the only part that matters is this inside, this argument inside, because that's where the time is. So if I want a minimum, well, I know that at a minimum, it's 0. Minimum magnitude, all right? You could say negative is a minimum, but I'm looking for the minimum magnitude, which is 0. All right, so I set this to 0. And I know that it cycles every 2 pi, where n is 0, 1, 2, 3, 4. All right, that's just where sine equals 0. So let's try 0 first. And I solve for, and I get t is negative 0.5 seconds, which means I travel back in time. Nope. No, watch that. We're not traveling back in time in this class. Yet. Probably never. Since that didn't work, I need to find a physical solution. Again, your answer always has to be grounded in reality. So my next case is going to be n equals 1. Oh, that's 2 pi. Let's see what this gives us. Run some math, solve for time. 33 over 12 seconds. That is good. because that's a real time. We can go forward in time. That makes sense. Now, key things, use the arguments if ever you're trying to solve anything for time, and then you can use your coefficients and everything you know about those to figure out your velocities and accelerations. I hope that helps. I will see you in class.